Raki, fellow teachers, potential teachers, dear students. I am very happy to be here with you this morning, and I want to congratulate the Vice Chancellor and his team for creating such a wonderful auditorium and to see a women's university prospering. I'd like to suggest to ACT that they should institute an award for women chemistry teacher researcher. They have done very well in chemistry, and we should provide exclusive encouragement to women teacher researchers in chemistry. Well, I am here to sing praises for chemistry. Why? So chemistry is in everything, and chemistry is everywhere. It is world's toolbox. There is nothing which happens without chemistry. In fact, our human body will not function without chemistry, whether it is oxygen, hemoglobin, or exhaling carbon dioxide. It's a separate matter that chemistry supports a $4 trillion per annum industry. And the kind of happiness it bestows on the society is difficult to describe in words. From anesthesia to relieving pain to getting rid of ulcers to bring happiness to get over depression and whatnot, chemistry is the one which comes handy. Imagine how the life would be, how miserable the life would be without the fruits of chemistry. I want to start by telling you that how chemistry manipulates. I mean, many times you describe manipulation of molecules on a grand scale. You see how organic transformations are done, and I'll give some examples as I proceed. But it's very difficult to beat nature. Nature is the most outstanding chemist that you can think of. From Taxol to optically active molecule, as simple a molecule as menthol. Same tree which gives you terpenes from alpha-beta guanine, delta-3 carrying, and similar tree giving you rubber. Now, all polymer chemists would find it difficult to emulate nature because at room temperature and at atmospheric pressure, you are able to synthesize natural rubber. And when we want to make synthetic rubber, how much trouble we have to take, how difficult it is to make synthetic rubber is for you to appreciate. Can you beat how silk is made? As a proteinous material, straight away you spin a fiber. There is no synthetic fiber that we know which chemists, chemical engineers are able to convert from monomer to fiber. So if you want anytime inspiration, look at nature and you will never be found wanting. So much so that when it comes to the flavors and fragrances, we don't even have a nomenclature. You will see jasmine-like, lavender-like, mint-like. We don't have a language of our own. When it comes to color, we can beat nature because we can produce any color. You can see in the audience very colorful dresses, Thanks to the produce of chemical industry, most major chemical industries first started actually manufacturing dyes and explosives. So I'll first give you some illustration of how chemistry manages things. You all know that we cannot split water into hydrogen and oxygen. Thermodynamics doesn't permit. The only way you can do it is that you should have an oxygen acceptor. So you can have so-called classic steam iron process. So iron is converted to iron oxide and you get hydrogen. But then there is electrochemistry. And you know that by electrochemical process, making water conductive by putting some alkali, we can split water into pure hydrogen and pure oxygen. Indeed, we had such one very large plant in Nangal when hydroelectricity was available for a paisa a minute in early 50s. Then you have the most stubborn molecule, sodium chloride. And you know there is no way you can split sodium chloride into sodium or caustic soda and chlorine, and electrochemistry comes to our help. And that we are able to electrolyze an aqueous solution of salt to caustic soda, chlorine and hydrogen. And I like to start with this as an example to show how innovations have taken place over the years. So I take you back first to a major breakthrough that came when soda ash was manufactured. That goes back to 1860s. When two most inert molecules, sodium chloride and calcium carbonate, were coaxed, and we could produce using principles of physical chemistry, because soda bicarb has very limited solubility. I am starting from this to tell you, long before chemical engineering was born, this process was perfected. And this same soda ash and same caustic, slaked lime available in the plant was used to make caustic soda. It was called causticization process. Then came in diaphragm cell. That was electrochemical. The diaphragm cell made big improvements with the diaphragm, asbestos diaphragm being replaced. Then came mercury cell. That also went out of the way when people found mercury can lead to poisoning, and Manitoba case in Japan really precipitated the case so much so that by next year no mercury cell will be left anywhere in the world. India, 90% of caustic soda is produced to the next generation, which is called membrane cell. Now look at the innovation in this membrane cell. It in a way owes its existence to space program. When Nafion membrane was developed, Nafion itself was a major breakthrough as a fluoropolymer, and it has extraordinary quality. It allows sodium to permeate but bounces back chloride ions. So you get absolutely pure caustic soda all the way up to strength going to 40% when Nafion as a membrane is not attacked. But prior to this we had catalyzed anode as titanium, ruthenium. Now we have catalyzed cathode. And not only that, now we have internal fuel cell that when hydrogen is not required, we are able to convert hydrogen into internal fuel cell and bring down the power consumption in a modern caustic soda plant. Not only this, we have now perfected industrially, globally, notably by a company called Bayer, when we do hydrolysis of aqueous hydrochloric acid to get back hydrogen and chlorine, so that chlorine is in total recycle in many processes where HCl comes as a product. And you would remember from your college chemistry that very, very long ago there was a process called Deacon's process to convert HCl to chlorine. That is no longer required because we can do electrolysis. Sulfuric acid is always called king of chemicals. But for a moment, going back to electrochemical process, one of the greatest innovations was making aluminium. And that was done by Hall. I always say, under most adverse circumstances of being helped only by a sister in a garage. Can you imagine alumina, a most stubborn molecule? No way you could convert the alumina, Al2O3, into aluminium. But Hall and a French scientist, independently, they were able to dissolve this alumina in cryolite. And cryolite at that time came from only one source in the world, Greenland, which belongs to Denmark. Now we have synthetic cryolite. And you could electrolyze this with a consuming anode of carbon. And carbon monoxide would come out and you could make aluminium. And for the amusement of many students who are there, when aluminium was first produced, it was more expensive than silver. And now today, nobody imagined that aluminium vessels will be used, pressure vessels, all our, so many of the items we use in every day. Apart from aluminium being an excellent conductor, you use copper only in very demanding circumstances, otherwise aluminium is used extensively as a conducting material. What I am trying to say is that chemistry does many things which superficially look impossible, but is converted into a possibility with some examples that I have given. Sulfuric acid, king of chemicals, used to be made by a polluting process called chamber process. It is now all made by the first catalytic process of the world called contact process, where SO2 and oxygen from air are reacted a vanadium pentoxide catalyst to give you SO3, which is then absorbed to make sulfuric acid. Sulfuric acid is very crucial to make phosphatic fertilizer. When I talked about food security, how chemistry has played such a vital role. We won't have enough food if we didn't have fertilizers, we didn't have agrochemicals. Chemistry has been crucial for apparels because if we didn't have synthetic fiber, poor person would not have been able to afford apparels. And particularly women from poor economic strata, they have been gifted with these polyester sarees which last and last and last, and look at their weight, look at how cheap they are compared to cotton sarees. I'll talk about these developments in a short while from now. But I also want to tell you that at this time, the greatest ever development in the history of chemistry came just around First World War, and that was Haber-Bosch's process for making ammonia. I am never tired of singing praises for this process for simple reason, not only because Haber got Nobel Prize and Bosch also got Nobel Prize, but for the fact that one could coax inert nitrogen and inert hydrogen to combine to give you ammonia. And that you needed supra-pure nitrogen and hydrogen and always in the stoichiometric ratio to make ammonia, because per pass conversion would be only certainly below 18% depending upon pressure and temperature. When ammonia was first made synthetically, the goal was not so much for fertilizer as it was for converting it to nitric acid to make explosives. We have just gone through the season of Nobel Prizes. Nobel required nitric acid to make TNT, and ammonia was required. And only source of ammonia at the time of soda ash process in 1860 was ammonia from coke oven gas removed by scrubbing in sulfuric acid and ammonium sulfate being reacted with slaked lime to give you ammonia, which was converted. What was wonderful about this ammonia oxidation is done on platinum rhodium gauze with a contact time as low as a microsecond and with 95% plus selectivity to amine. So nitric acid made a world of difference because the only source of making nitric acid was Chilean saltpeter, and nobody could have fought a war. But leave out war, we cannot do any mining without explosives. So, explosives may be used by terrorists, but explosives are absolutely essential for mining ores, because you cannot mine ores without using explosives by and large, except some open pit mining. But even there you need. So this ammonia business was a fantastic thing. Then came discovery of crude oil, and crude oil then provided. So two good things you can say about chemistry. You cannot be mobile without rubber. Two, you cannot have mobility by fuel without having crude oil. So crude oil is fractionated, and every fraction has a use from the top to the bottom, which is asphalt. And you know asphalt roads, and how asphalt is modified, how chemistry is used to convert this asphaltene into molecules which have better adhesion with the so-called metal, that is our stone wool. This petroleum refining changed the scenario in the world completely. And arising out of this, the need for petrol kept on rising because automobile revolution came in. By the way, automobile is very, very intimately connected with chemistry and chemical. You see every part of an automobile, from the high quality paint to bumpers to the dashboard, everything is a produce of chemical industry, in turn dependent upon chemistry. So you may say automobile, but it is all a gift of chemistry. Just as this all-inclusive growth through mobile phone is really a gift of chemistry, because everything that you see in a mobile phone is a produce of chemical industry based on high-level chemistry, including LED. Imagine when LED was invented, people did imagine at that time that LED will come to every home, not only through mobile but through illumination, which reduces the power consumption drastically. What 10 watt can give you, you cannot get with 100 watts with a normal lamp. So LED, you can see for yourself how LED would have been possible without gift from chemistry. Chemistry is crucial for biology, chemistry is crucial for material science. You see, in terms of material science, you can give a classic example of carbon. You have activated carbon, you have graphitic carbon, you have of course diamonds, and now you have graphene. So you see, simple C of carbon, manifestation of this in different ways, which chemists have managed to manipulate. We make synthetic diamonds. I say it's an expensive process, but synthetic diamonds are produced under high pressure conditions, simulating what might have happened in nature. But I want to give you as a kind of little departure one or two very simple examples, because you are having education in chemistry and all. How exciting it is to teach chemistry, because you can link it to everything in daily life. But I want to give you just two simple examples to tell you how we manage to chemistry some very simple things. Well, but take marble, grind that marble, sparkling white marble. That ground calcium carbonate will be useless in the toothpaste. So we have to convert this calcium carbonate of any grade into calcium oxide by what we call calcination, and recarbonate that to give you precipitated calcium carbonate, which you are using in toothpaste or filler in polymers, filler in rubber, and the ubiquitous Xerox paper that most people don't realize has 10% by weight of precipitated calcium carbonate. But you couldn't have used ground calcium carbonate. An analogous example is quartz. You say very beautiful silica. You know, silica manifests itself in so many ways, including with very expensive rubies and all. But quartz you would have thought was an epitome of silica. You grind that quartz, it is no good for transparent toothpaste, like close-up or the Colgate gel. You have to convert this to sodium silicate, precipitate out silica. In the case of calcium carbonate, we could manipulate conditions of carbonation to give you different crystalline habit, calcite, argonite, mixture. Silica is somewhat different, and you get precipitate silica. And in both the cases, we have now gone to nanoscale. Commercially, we produce thousands of tons of calcium carbonate in the nanoparticle size range, because the pigmenting power of that is far superior to coarser calcium carbonate. Similarly, precipitated silica. Now revert to what something else happened in 1920s, 30s. There was a revolution in Germany with rapid chemistry. The acetylene in turn based on an inorganic chemistry, calcium carbide. Acetylene made just about everything you could think of. Vinyl chloride, vinyl acetate, ethylene, vinyl ethers, name it. All of it is almost extinct now, because everything is based more or less now on ethylene. But the revolution that was brought about by Rappe was absolutely and truly extraordinary. And one should pay tributes to this great chemist Rappe, that he was able to do such wonderful things with acetylene chemistry. We still use that for some industrial processes, like acetylene is condensed with formaldehyde to give propagated alcohol, butanol, and hydrogenate them. Some things are still done with acetylene. And in China, because coal is plentiful, power is very low cost, they still have calcium carbide based TBC, which nowhere else in the world in any sizable quantity is practiced. So this Rappe chemistry brought in a major revolution of turning around inorganic chemistry into organic chemistry, and failure of thermodynamics to prove that calcium oxide plus carbon doesn't go to calcium metal, it lands up in calcium carbide. Now I want to tell you two most outstanding things that happened in 1930s, which have no parallel apart from ammonia, and it was the discovery of nylon. how nylon was invented is an illuminating chapter in the history of chemistry, because Crothers was invited by DuPont to do something very original in high molecular weight molecules, polymer. And this nylon revolutionized at that time many things, apparel wear including. But most notable was, just after war, nylon socks became so important because, since it's a women's university, I must tell you this example, that in Europe and America, women were not working in offices. They were all wearing long dresses and all. After Second War, because of shortage of men, women started working in factories and all as secretaries and whatnot. And then they had to wear skirt. This is called skirt revolution. And when you wear skirt in winter time, you have to wear stockings. And these stockings used to be of silk, which will very frequently have holes. And they were then replaced by nylon stockings. And apart from nylon being used in wartime it was very critical because parachutes used nylon. Then nylon became a very popular thing for engineering purposes, and you know that all zips are exclusively nylon, no longer in steel. And that finally you see nylon as an engineering nylon in terms of bulletproof chest through the Kevlar. So this nylon, what we call in the history of chemistry, chemical technology, archetype of a discovery-driven product, finally buttressed by market-driven. Though the demand for nylon for apparel wear disappeared to a great extent after polyester was invented, around similar time, simultaneously by ICI and DuPont. And polyester then went into fantastic range of things, from bottle to film, name it, and polyester was around. Then polyester cotton blend. Nylon was not easy to blend. Polyester could be blended with cotton, could be blended with silk, could be blended with wool. Extraordinary development which has made a big revolution in India. Today, as you know, synthetic fibers have overtaken cotton because cotton fibers are too expensive, not easily affordable, because very expensive to maintain. Around the same time, since many developments in history of chemical industry were serendipitous, they were by accident. Polyethylene was invented by ICI in 1930s. And many of you would be really amused to hear that this polyethylene, apart from everyday use that you find in packaging, it was such a fantastic insulating material, and this will come to surprise many, that it was this polyethylene which allowed radar to function. And you know how Second War, radar was so important because insulating, no other insulating material did that job for that high frequency radars. It's an unbelievable thing, but polyethylene was used at that time for insulation of radar. Now polyethylene today is the highest volume polymer in the world, followed by polypropylene and many other polymers. But look at the beauty of this polyethylene. Ultra-high molecular weight polyethylene can be converted into fibers which are used for reinforcing cement concrete in aggressive atmosphere around coastal lines, around the oceans. When the steel rods, even though coated with epoxy resin, cannot stand the atmosphere. We have commercial ultra-high molecular weight polyethylene fibers for reinforcement of concrete. A very novel development. Now, I jump to Second War. In Second War, as I told you, no mobility without rubber. And all rubber was denied to Allied forces because rubber was all blocked by Japanese. So America launched this program to make synthetic rubber on a grand scale. So new processes for styrene, butadiene had to be developed. Germans had, but Germans were fighting the war. Germans called them under the brand name Buna. Buna S means styrene, butadiene rubber. Buna N means butadiene acrylonitrile rubber. And that this synthetic rubber today, which completely outweighs natural rubber, in the global scene, 2/3 is synthetic, 1/3 is natural. It's funny that natural rubber is good for cold climate and synthetic rubber is good for tropical climate, and all natural rubber is grown in tropical climate. This is how nature. The Second War saw these extraordinary developments. But two other developments I want to tell you which have changed the history of entire aromatic chemistry. Earlier, benzene, toluene, xylene, phenol, pyridine all came from coal tar. In fact, it was called coal tar chemistry, coal tar dyes. Coal tar provided most of these, and today their contribution is next to nothing. So benzene, toluene, xylene, if we didn't have paraxylene, we will not have polyester fiber. If we didn't have benzene, we won't have phenol. So phenol formaldehyde resin, we won't have bisphenol, we will not have polycarbonate. If we didn't have cyclohexane, we won't have nylon 6, and so forth. So what was done at that time? In order to get gasoline of high octane rating, one had to reform linear molecules. So hexane must go to benzene, heptane must go to toluene. Now imagine how difficult it would be if you ask an undergraduate student in chemistry and give him a riddle that can you convert heptane into toluene? Immediate answer would be no. You got to crack. Nothing will happen. But here came the platinum catalyst based process, and two people who worked very assiduously on this, Patrick and Hansel, they finally found their place in Hall of Fame in Washington. Now, if this platform process was not developed during Second War, we would have been starved of benzene, toluene, xylene, and you can see the consequences of not having benzene, toluene. Toluene is also required for TNT. The amount of toluene that was available from coal tar was too small for the requirements of even TNT. Forget about TDI, toluene. Urethanes, a great development. And you see urethanes in such common items like U-foam to all our great shoe polish, urethane. Now instead of PVC leather cloth, the urethane ones, urethane for even in our wear, we want very cold climate, the inside jacket is made out of urethane. So you see for yourself how great has been the innovation of urethane, subsequently polycarbonate, and polycarbonate has gone into all kinds of things as high impact resistant. But before this polycarbonate came in, there was a major development of transparent plastic in the form of brand name of ICI called Perspex, simultaneously developed by DuPont with the brand name Lucide, polymethyl methacrylate. And how this transparent plastic made a world of difference for display systems and for varieties of other applications, including chemical engineering research, because you could make vessels in Perspex where you could see things happening. Now, I want to digress a bit and tell how chemistry made an impact on quality of life. I only alluded about anesthesia, drugs for ulcers, drug for cholesterol. Now you see how atorvastatin became a $13 billion drug, and most recently a major breakthrough in treating hepatitis C. But don't forget what came through antibiotics through sulfur drug. Penicillin, streptomycin. Many of you may not remember that up to end of 40s, early 50s, a lot of people were dying of TB in Europe. There was no cure for TB till penicillin was produced on large scale and streptomycin in 40s. So many incurable diseases were taken care of by novel developments of antibiotics. And this goes on and on because you keep on having new diseases, and look at how vaccines made a major difference to quality of life. When a politician says, what has science done? I always give two examples. One, this ubiquitous mobile phone which everybody carries these days. It is prestigious when I say no to have a mobile phone, and other is vaccine. These are the two things which are made, and both are very intimately connected with the produce based on chemistry. As I re-emphasize, life will be miserable without chemistry. I think teachers of chemistry should take this as a vision to extend to people, because people only talk of some accidental leak of chlorine, or now people adore gold. But don't forget, gold is not possible to make without cyanide. Now if you use cyanide badly, then you say, and you curse, at the same time you sport gold. Now nobody has developed a technology of making gold without cyanide so far. I will now turn my attention to few other things. First, which has made a major difference, and to the development of principles of physical chemistry, osmosis, principles of polymer chemistry, and everybody now, even the laity, the common person knows a thing called RO. They may not know the full, just as most people won't know what is SMS from, what is the full form of SMS. So most of these people who say RO ka pani hai, but they won't tell you what is RO standing for, reverse osmosis. How reverse osmosis has made such a major impact on quality of life, because seawater and brackish water is converted into high quality potable water. Today just about every home has RO units. But look at what chemistry did, both through principles of physical chemistry, osmosis, and through polymer. First in terms of sheets, and now in terms of hollow fiber. And finally this hollow fiber had a great impact on nephrology for all dialysis patients, where you use hollow fiber for purification of blood. So see for yourself what impact we have made only through RO. Now we have an extraordinary development. We have gone far beyond RO, because we have nanofiltration. The nano is a very fashionable word these days. But here nano is used in a different context, that you are able to knock out molecules with molecular weight more than 250 from everything else. So it is making such a major impact on pharmaceutical industry and agrochemicals. While on agrochemicals, I just want to tell you 2-3 examples. One is much abused today, DDT. But please don't forget, DDT was a major breakthrough and saved millions of people suffering from malaria. Millions of people in the world were saved out of DDT. And today the persistent variety DDT is again recommended for specific applications by WHO. But how our journey has gone from DDT to malathion to the most modern insecticides in the form of pyrethroids. Learning from nature how pyrethrum flower gives you pyrethroids which are photo-unstable, so they don't have longevity. Synthetic chemists were able to convert them into photostable. So whether you had penvalerate or many other varieties of pyrethroids that came in, and they were used at a level of less than 1% of DDT or malathion. So you see for yourself what major impact we have made. But if I want to dramatize this, I will give you the example of weedicide, herbicides. The naked eye in a flooded field cannot distinguish between a weed, herb or the main plant. The weed and herb takes up fertilizer in disproportionately high rate, so they grow much faster than the main crop. Now how do you get rid of these weeds and herbs? Chemicals have eyes. So chemicals come handy, and they are systematically eliminating weeds and herbs. And they are a major revolution in the history of agrochemicals, because we use them today. Modern molecules are used in only few grams per hectare. Few grams per hectare. That is the potency that we have of new generation of weedicides and herbicides. And then when you have volucides, and you also have this soil-based diseases. So we have now pyrethroids which can be used for soil pests. Molia, this nematodes in Rajasthan, they are called molia, as dangerous as a dangerous monkey. Now very difficult to get, a lot of crops get lost, but we have got very good nematicides which take care of nematodes. Now let me jump and tell you something. I told you about many catalytic processes, but I want to take 2 or 3 examples. One is how we have been able to beat nature, or at least compete with nature in making optically active molecules, and how they have been rewarded with Nobel Prize. So we are able to create, and one of the greatest development was this agrochemical dual magnum, which is today produced at the level of 20,000 tons per annum, optically active. Before that, only of optically active molecules which were done commercially by synthetic process were L-DOPA, Parkinsonian disease drug. Today, many other optically active molecules are produced, including phase transfer catalysis using zirconium. This has been an extraordinary development. What you will find in the history of chemical industry, chemistry, large number of Nobel Prizes are gone to people. It's not only asymmetric synthesis. And I am always very charmed by meta-thesis, where also they were rewarded. It actually first occurred in industry, Philips, then and in France, then of course DuPont people, and then Grubbs. Now what is this great thing about the meta-thesis? Imagine chopping a molecule and stitching that. It started first with excess propylene in industry. Today propylene is deficit. I'll tell you this amusing story, that you could take 2 moles of propylene and split them into ethylene and butane. You tell any undergraduate student in chemistry, can you do it? Emphatic answer will be no. So this was done commercially, and today we do reverse, because we have great demand for propylene, so we take butene to an ethylene and produce more propylene commercially on scale of few 100,000 tons per annum. If you take world as a whole, 500,000 tons by this meta-thesis. And same meta-thesis has been taken to sophisticated organic chemistry, and you will hardly find these days learned journals not having some papers on asymmetric synthesis, some papers on meta-thesis and so forth. Now, in the realm of homogeneous catalysis, 2 outstanding developments took place. Both of them were rewarded with Nobel Prize. The hydroformylation reaction, so-called OXO reaction, where Wilkinson got Nobel Prize. Propylene plus carbon monoxide plus hydrogen going to butyraldehyde. First invented with cobalt catalyst running at few hundred atmosphere, and with rhodium-based catalyst, thanks to coordination chemistry, this works at 40 bar, 50 bar. And carbonylation of methanol to acetic acid, which completely revolutionized manufacture of acetic acid. Imagine CO plus methanol, which used to be done with cobalt carbonyl catalyst at 600 bar. With rhodium catalyst, it is done at 30, 40 bar, 50 bar. Not only that, methyl acetate plus carbon monoxide goes to acetic anhydride. Fellow teachers and budding students, I can go on and give you many fascinating stories, factual, where the charm of high science, the charm of teaching the subject of chemistry, chemical technology, industrial chemistry, its utility in everyday life, and the impact it has made on society, I can go on and on. I have attempted to give you a flavor, just to tell you that no matter what you want to look at, chemistry is central. And I told you it's world's toolbox. It is the solution for many problems that we face in society. With that, may I say that you enjoy your stay here, enjoy teaching chemistry, encourage more lady students to come to teaching and research, and please make sure that next year we will be given award.
As a token of our heartfelt gratitude, which will also serve as a fond remembrance, I invite Dr. Ashok, Professor M.M. Sharma. Thank you, sir. I also request Prabhu. Professor Pradeep Bhatnagar to present a memento to Dr. Brijesh Parekh. Thank you, sir. I now invite Professor Rakhi Gupta, conference convener, to propose a formal vote of thanks.
Dr. Ashok Gupta, Honorable Vice Chancellor, the IIS University, Padma Vibhushan, Professor M.M. Sharma, keynote speaker at the inaugural session, Professor S.D. Samant, President, ACT, Dr. D.V. Prabhu, General Secretary, ACT, Dr. Vijesh Pare, Vice President, Central Zone, ACT, Professor R.K. Bansal and Ms. Manisha Patni, conference co-conveners, Professor Pradeep Bhatnagar, Dean Faculty of Science, the IIS University, all the esteemed invited speakers, participating delegates and guests in the audience. It is my proud privilege to propose a formal vote of thanks on behalf of the IIS University, Jaipur, at the inaugural ceremony of the 3-day National Conference on Emerging Areas in Chemical Education and Research and National Convention of Chemistry Teachers, NCCT 2014. The conference has been planned keeping in mind the promotion of teaching and training by way of knowledge sharing. As is apparent, the initiative has brought together a host of chemistry teachers, researchers, and industry personnel from both India and abroad. Of course, we were expecting, but some of them could not make it. I am confident that these 3 days will provide an ample opportunity to one and all to exchange their views and research ideas. I'd like to express my deep gratitude to Professor M.M. Sharma, sir, for so very kindly acceding to our request to deliver the keynote address. Thank you, sir, for your presence and insights. Your address, sir, has set the tone for the deliberations that are to take place over the next 3 days. In fact, the wonderful examples that sir has quoted today, that how chemistry can impact our life, will surely motivate some of the young budding students, chemistry students, to pursue research in that direction and make the world a better place to live. I take this opportunity to thank Professor S.D. Samant and Dr. D.V. Prabhu for giving the IIS University this opportunity to host the annual convention of ACT in the big city, Jaipur. I acknowledge with gratitude all the help and guidance extended by them which helped us to plan this event, keeping in mind the minute details. At this juncture, I would also like to acknowledge Professor Sudha Jain, past President ACT, since it was during her tenure that the proposal had initially come to us. I am thankful to all the invited speakers for taking time out of their busy schedule to be here and consenting to speak on contemporary topics in chemistry. Thanks are also due to all academicians, delegates, and students who have come from far and wide to attend the conference. I sincerely hope that your inputs and interaction during the course of this conference will make new contributions to the field and will be of immense value in times to come. My thanks are due to Dr. Ashok Gupta, Honorable Vice Chancellor, the IIS University and Conference Chairperson, for his unstinted support and invaluable guidance throughout, which has given this 2-day event its present shape. May I take this opportunity to convey thanks for the help and support extended by the head, Ms. Manisha Patni, and senior faculty members, Dr. Pragya Sinha, Dr. Varsha Goyal, and other colleagues from the chemistry department, and of course other departments. The smooth conduct of the event would not have been possible without the team spirit and all my colleagues' help, support, also rendered by student volunteers, research scholars, and the technical and support staff. Lastly, I thank all the media persons whose ample coverage of the conference will bring this contemporary issue closer to public interest and notice. We also acknowledge the financial support by the Department of Science and Technology, New Delhi. With the hope that this conference will accomplish all its objectives, I wish it all the best and welcome all the delegates. Thank you all.
Faculty members from the Department of Chemistry at the IIS University to please come up on the stage for a group photograph.
आगे आ जाओ थोड़ा।
Session is Professor P. Pramane, International Journal Institute, and has undertaken a number of research and development projects. His areas of interest are nanotechnology and material science. He has guided almost 56 PhD students and received medals for Chemical Research Society and Material Research Society. He has also organized various community service programs and contributed to academic environment as a member of various board of studies. Professor Pramane is a member of several professional bodies such as the Indian Society for Technical Education and Textile Association of India, to name a few. He has also been the recipient of the Best Teacher Award twice. Professor Pramane is currently working in the Department of Applied Chemistry, IIT Kharagpur. We welcome you, sir. May I now request Professor R.K. Bansal to award floral greeting and token of our appreciation to Professor Pramane. Thank you, sir. The speakers of this session are Professor Uday Mitra and Dr. Samita Lalvi. I would now like to request the speakers to take their seat on the dais.
Good day to you all. This is the first technical session will be presented by a very famous national scientist, Professor Uday Mitra. I know him personally for a long time, possibly when he joined PhD program. At that time I was a young lecturer. He did his PhD and become Professor, Department of Organic Chemistry, Indian Institute of Science, Bangalore. He received so many awards and honor from various national and international community. He was a fellow of Indian Academy of Science, Bangalore, initiated a long-term research program at ISC on the novel chemistry of bile acids and pursued research in the general area of bile, acid-derived, dendritic structure, functional and hybrid nanomaterials and hydroorganogelators. In this area, he is one of the leading scientists, I should say the only scientist in national level. And this research was highly appraised from the outside of the India and inside India also. His interest in chemical education is a very long story, and he has a very big group of researchers in the Indian Institute of Science. His research team is quite reasonably large, possibly maybe 15 or 20 students are working together. He is an active participant in workshops of various teachers and students organization by Indian Academy of Science, organized by NCCT and other organizations. And he is very active particularly for chemical education, promotion of chemical education in India. He has published 90 research papers in international journals and wrote several chapters of books which are very, very important, particularly in the field of his organic chemistry. He is recipient of many prizes and awards, and few are mentioning. He received Bronze Medal of Chemical Research Society of India 2000, Millennium Medal Indian Science Congress Association in 2000. He is one of the SS Bhatnagari awardee. He received Professor T. Navneet Rao National Best Chemistry Teacher Award in 2005. Then he received CDRI Dal Research Award in 2006. A.V. Ramarao Foundation Prize Lecture 2007. And the last one is MRSI Medal 2008. He is a Desi Bose National Fellow, and I request Professor Moitro to come to the dais and present his lecture.
Do I still have my 45 minutes?
I request Dr. Rakhi Gupta to present floral greetings to Professor Uday Mehta.
Can I pause my timer? I've stopped my timer. Thank you. Thank you. Let me restart my pause timer. And thank you, Professor Pramanik, for the very generous introduction. And let me also thank Professor Bansal for giving me an opportunity to visit and give a talk to this NCCT. What I would like to do is to give you some of my thoughts which have been put together during the last almost 10 years. This particular talk was first started in IIT Kanpur in the CRSI meeting, and from that time it has undergone several sort of upgradations, and what you are going to see is the latest version. However, I have added a slide after listening to Professor Sharma, and that is because he mentioned about anesthesia. It turns out that today is sort of an anniversary for the first use of ether as an anesthetic in 1846. So I thought I will share this information with you. Professor Sharma also mentioned about ammonia synthesis. Most of you have studied this, taught this, but I thought I will show you one of the first reactors that they were used in Germany. And here it is just outside the BASF facilities in Ludwigshafen in Germany, which was photographed last year. So it's actually quite tall, as you can get a feel for the scale by looking at the size of this gentleman standing there. Before I start, I would like to, since there are lots of students, I would like to emphasize the point that learning is a process which is not a one-way process. A teacher from a student, or a textbook to a teacher, or a textbook to a student. You need to ask questions. Unfortunately, this is something that is frequently ignored in our educational system. Our students only learn to answer questions. So therefore, it is very important to ask questions. And I would like to quote a couple of very famous chemists on this issue. Professor Richard Sayer, who is a professor in Stanford University. Am I doing something funny with the lights? Okay, I think this is fine. He mentioned that the quest to answer a question is where the learning takes place, not the answer itself. So, for more details, you can read this particular article in CNN News a few years ago. I would also like to state a statement from this gentleman, and I will disclose his identity in a minute. He said that my mother made me a scientist without ever intending to. Every other Jewish mother in Brooklyn would ask her child after school, so did you learn anything today? This is a very standard question we ask our children when they return from school. He said, not my mother. She would say, did you ask a good question today? And then he says, that difference, asking good questions, made me become a scientist. And now let me tell you who he was. He was I.I. Rabi, professor of physics in Columbia University, and he got the Nobel Prize in 1944 for discovering NMR, nuclear magnetic resonance. And the rest is history. So for the students, I have a question to ask. You all have heard about heavy water, right? You all know about heavy water. Heavy water is D2O. I would like you to think during the next 40 minutes about an experiment I can do to demonstrate to high school children that D2O is heavier than H2O. I would like to show an experiment by which it can be shown that D2O is heavier than H2O with the conditions I will give you only 3 milliliters of B2O. I will give you 12 rupees, and you can use any apparatus available in your school lab or in your kitchen, in your mother's kitchen, and so on. Okay. So think about it. I want to do an experiment, not using a balance, showing the density by measuring 3 ml of H2 and D2O. That's a lousy experiment. I would like to demonstrate a very nice experiment by which you can prove this. So you think about it, and I will try to give you my answer towards the end of my talk. Okay. So here's the point. The computers have made things very easy. When I first designed this talk, we were still in a slow internet age when most of the access was through dialing connections. Some of you probably are not even aware of it. Now everybody has a mobile phone with high data speed, 3G access and so on. So access to data has become very easy. But what has also happened is that much of the data perhaps is sometimes useless. For example, people say, this t-shirt says we are drowning in information but starved for knowledge. So my purpose today is, from this huge amount of information, how do you extract chemical knowledge? Okay? So I have done a little bit of research on this, and therefore I would like to share with you the information. And my talk will be available as a PPT file or a PDF file, whichever way you know. So you don't have to write down any of the links here. And this is kind of like a funny picture which shows that kind of information we have to deal with to kind of sift through the information to get what we want. My office is not as bad as this, but it's actually bad enough. Okay? All right. So what I would like to do is to highlight to you some of the chemistry-related links which provide useful information. And I have updated this and I've checked all these links are valid till today morning. Okay? But since I was not sure if I'll have internet connection here, I've only taken a picture of the website, and that I would like to show you. One of the nice ones for links for chemistry is the University of Liverpool in UK, and the website looks like this on a screenshot. Okay? And chemistry.org.uk, and that provides a lot of information. I will, because of time restrictions, I will not be able to go through every single detail. But here are some information. If you are looking for organic chemistry information, the ACS, American Chemical Society Organic Chemistry Division, is also very useful, and they provide a huge amount of information. Again, I will not go through the website and show you what information they contain, but that's a useful thing to have. And one of the things they have is a link to University of Wisconsin-Madison, where you can get a lot of information about organic data. And here is one particular screenshot. You won't be able to see it. Okay, that's not the purpose, but basically this is a table for pKa, table for NMR chemical shifts, and everything that you may need for teaching or learning. Particularly some of the organic chemistry aspects are all available there. Sorry. RSC, Royal Society of Chemistry, has on this particular website, excuse me, my computer is new and I'm still getting used to it. In this section, they have chemistry education information at various levels, starting from high school to middle school, high school, undergraduate, postgraduate, PhD. So this will be useful for students at different levels. Science is fun. This is again University of Wisconsin website. That's a very useful thing to have. But I would like to show you a contribution made by our colleague Professor K.L. Sebastian in the Department of Inorganic and Physical Chemistry, and this is hosted in the Indian Academy of Indian Academy of Sciences website. And again, I will show you an offline version of this. I often joke that Professor Sebastian, being a physical chemistry at the top and organic chemistry at the bottom, but jokes apart, if you click on any one of these, for example, if I click on physical chemistry, I will see the entire UG syllabus, UGC supported syllabus at the UG level. The entire thing is listed. Okay? And every topic has a link, and clicking that you can access more information. Regrettably, all the information goes to UK or to USA. There is no Indian content in the information. But what And I think that is something that we all can work together to have a repository of, quality study material, not only in chemistry but in other subjects as well. But that will require a coordinated effort, and that's besides what I can speak today. But for example, structure of matter, quantum mechanics, quantum theory, rotational motion, and as I said, if you click on any one of these, it takes you to an external website where you can get more information. I will not go through all of it, but what I would like to quickly show you is similar things exist for inorganic chemistry, okay, and also organic chemistry. Okay, these are some of the topics. I will show only from the top couple of pages. Again, a lot of information you can access through this particular website, and that's located in the Indian Academy of Sciences website. So it's very useful. There are a few others that I would like to show you before, we are also going to have a little bit of fun, particularly since there are a large number of student participants here. One of them, for example, is periodic table. There is a very nice website called Web Elements. If you want to know specifically about the information about certain elements, webelements.com is a very useful source, because there are literally thousands and thousands of periodic table resources available on the website, and the periodic table has been, as you perhaps know, has been modified in various different forms, starting from Mendeleev's, very limited periodic table. You have spiral periodic table, circular periodic table, cylindrical ones, and so on and so forth. Again, because of time, I will not go into it, but you can click on some of these. If some of the students are interested in classic chemistry, for example, if you want to look at Wohler's original 1828 paper, this is a website which is useful. Classic chemistry by this Carmen Giunta, that lists a lots of classic papers. For example, if you want to look at Haber's original paper on ammonia synthesis, you can go there. Students of organic chemistry are always fascinated by name reactions. I should also point out at this time that many website links are not always invariable in the time axis. Some of them change as a function of time, particularly the commercial ones. So there was a site called ChemPen Software which listed about 400 organic name reactions, but a couple of weeks ago I found that that site doesn't exist. So the one I found is here, where there are about 145 name reactions available, and you can take a look at it and get the original references, and that's very useful. For those who want to do organic experiments, there's a very nice website I found in Rochester which is called NVD. It essentially means it's not voodoo. Okay? So chemistry experiments are useful, and I'll just show an offline version of it so that you have some idea. This is not voodoo X, okay, whatever that means. But it has got very, very useful information about things that you can do over here as well. Chromatography, heating and cooling, practical things that a student does in an organic chemistry laboratory. So it's a very useful website as well. Okay. And finally, there is another one called Molecule of the Month, which is located in Bristol in UK. Try to locate my mouse, which lists a variety of interesting molecules. These are not new molecules. These are molecules which you and I know very well. For example, it can be something as simple as bisphenol A, Wilkinson's catalyst, and even ammonia. Okay, and these were contributed by various people, and I'm sure that any of you can also have their information, collect it, and submit them. And if they find it useful, they will publish it as Molecule of the Month. But if you click on any one of these, you can get huge amount of information about such interesting molecules. Okay? And again, this I thought was a useful site to look at. There are many, I think Professor Samant mentioned that we don't do very many experiments. Students don't do experiments, and those who come after MSc, they are not very well qualified in terms of doing chemical experiments. Lab practicals are not done properly. Professor Kelkar will elaborate on it, about the importance of doing things small. on a small scale. But if you would like to see experiments being demonstrated, these are the two sites. I'm not sure if I have the screenshots or how.